Hello everyone, my name is Guangyang Fang. I'm a research scientist at the University of Maryland. I'm the PI of this VR project. Today, we're going to show you how to use our latest version of the VR software.
Hi, my name is Ashmita Pine, and I'm a sophomore at the University of Maryland, College Park studying computer science. In this project, I've had the opportunity to learn Unity, as well as work on projects outside of just the classroom.
Hi, my name is DJ Figueroa, and I'm a sophomore computer science student here at the University of Maryland. I'm also one of the virtual reality developers working on building this weather visualization application.
Our project investigates the well-known El Niño and La Niña weather phenomena. These are climate patterns that periodically warm and cool the equatorial Pacific Ocean and affect global weather patterns. El Niño and La Niña make up phases of a cycle called the El Niño Southern Oscillation, or ENSO for short. These phases alternate every few years, where the El Niño phase has warmer than usual sea surface temperatures, and the La Niña phase has cooler than usual temperatures. To help visualize El Niño and La Niña, we upgraded our previous virtual reality weather visualization application and redesigned its control panel to make it easier to use. We have implemented a series of long-term oceanic climate datasets from 1901 to the current day to demonstrate historical ENSO events over time. In our datasets, we include two types of sea surface temperature data, or SST data for short: optimum interpolation SST and extended range SST. The optimum interpolation data has a higher resolution of sea surface temperature data, whereas the extended range data has a greater time span of the data. We also visualize other data such as sea surface wind stress, thermocline, precipitation, and outgoing long-wave radiation, or OLR for short. These datasets and their anomalies are listed on the sidebar menu on the left. By clicking any of these datasets, an inspector panel will appear on the right, which shows the dataset's brief description, visualization controls, a legend for interpreting the data, and other metadata related to the dataset. In the middle panel, there is a map view that displays a 2D representation of all the visualizations. Beneath that, there is the timeline which controls the temporal playback of the data selected, and you can also display a precise date by clicking the Date Selector button. For example, December 1988 is the strongest La Niña event in history, and December 1997 is a very strong Eastern Pacific El Niño event. There are also a series of quick controls at the very bottom which help to manipulate the globe and its visualizations, such as the cut tool that we'll demonstrate later. We will also soon be restoring the pencil and measuring tool to allow for annotations on the globe like in our previous weather application. With virtual reality, we are also able to intuitively demonstrate the thermocline behavior of ENSO. Let's examine the El Niño thermocline by using the cut tool to take a cross-section of it across the equator. As we can see, there exists a transition layer between warmer mixed water at the ocean surface and cooler water down below. During this time, the Eastern Pacific warms up, the trade winds weaken, and the thermocline becomes abnormally deeper. This depresses the upwelling of the cold water from the deep ocean, which makes the region even warmer, and this is sometimes referred to as Bjerken's feedback. Now, let's introduce how we can use our virtual reality application wirelessly and remotely on our central computer within the Proving Ground lab here at CISSS. We believe that the ability to remotely stream this application will be highly beneficial for remote education and training in virtual reality. Let's look at a demo of how this would work. Suppose I am the student and I am learning from my mentor Dr. Fang and that we are at different locations. Dr. Fang begins by logging into the central PC with his MetaQuest via virtual desktop and interacts with our virtual reality application running on our lab computer. I am able to watch his perspective by using a screen sharing application like Zoom. In this demo, we use the virtual reality streaming software Virtual Desktop, which only allows one user at a time. Therefore, to try it out myself, Dr. Fang disconnects first so that I am able to log into the lab computer with my MetaQuest. In this way, users would be able to log into the server anywhere, as long as they have a stable internet connection. This makes our VR application more accessible to those who lack the powerful computer hardware currently needed to run our application. Currently, we are exploring more effective ways to offer remote virtual reality education, such as a custom virtual reality streaming client and a multiplayer standalone application for the MetaQuest that wouldn't require any external PC. Additionally, we are working on real-time processing of weather data, which could allow National Weather Service forecasters to improve their forecasting skills and better understand and analyze their weather events. Thank you for watching, and we hope you'll be able to try our application soon.
In late August, early September of 2019, Hurricane Dorian tracked westward across the northern Atlantic Ocean and then northward along the east coast of the United States. On September 1st, Dorian became a Category 5 hurricane with sustained winds up to 185 miles per hour. A loop of imagery from NOAA's GOES-16 satellite shows where the tropical cyclone can be identified by its buzzsaw-like shape and definitive eye. While near peak intensity, Dorian made landfall in the Bahamas, becoming the strongest landfalling hurricane on record in the Atlantic Basin, outside of the warm waters of the Gulf and Caribbean. Using tools within this virtual reality software, we can outline the extent of the moist clouds within the hurricane and measure its diameter as about 600 kilometers across. Virtual reality, or VR visualization, allows for three-dimensional investigation of atmospheric data in a user-friendly environment. For example, we can take a cross-section of derived cloud top heights from the GOES-16 satellite. This view can be adjusted in time and space. The experimental satellite product Average Layer Precipitable Water identifies the rich moisture in the atmosphere out ahead of Hurricane Dorian, which will allow it to maintain its incredible intensity. This VR software combines several data sets, including upper-level wind vectors from the Global Data Assimilation System, which can be plotted and customized, as well as radar reflectivity showing heavy rainfall. After its landfall in the Bahamas, Dorian proceeded to move painfully slowly through the island nation. As a result, it became the costliest tropical cyclone in their history. GOES-16 water vapor imagery shows a strong trough of dry air over the southeast United States, halting Dorian's westward progress and eventually causing it to drift northeastward, which we can outline using the drawing tool. Further research continues to develop the operational value of unique data visualization using the VR technology so that scientists and forecasters can better understand severe weather events.
On February 14, 2019, an atmospheric river, or AR event, occurred in the eastern Pacific Ocean and impacted the western coast of North America with severe precipitation. Here we show a loop of imagery from NOAA's GOES-17 satellite, where a long corridor of clouds is identified stretching from the tropics to the California coast. This same feature can be observed in the infrared imagery, where dry areas are red and humid areas are blue. We pause the loop to measure the extent of the AR. The corridor of moisture stretches over 4,000 kilometers from 12 degrees to 37 degrees latitude. Next, we display NOAA's ALPW data product, showing moisture in the atmosphere. Typically, scientists and forecasters can only see the 4 layers of data shown on your user control panel, but with virtual reality, we can estimate the amount of water at a continuum of altitudes. For another perspective, we take a cross-section along the length of the moisture corridor and enter a surface viewing mode. From this angle, we identify high moisture content at all altitudes in the atmospheric column. Now we overlay wind vectors from the GDAS system. Here we observe high-velocity winds at all altitudes pointing the same direction downstream. This causes the transportation of moisture comparable to stream flow in a river on land. Exiting surface mode, we display a set of points from the NuCAPS dataset. This dataset maps the vertical profile of temperature and humidity in the atmosphere. Forecasters can use this data to help predict the amount of rain that an AR will produce when it impacts the land. Notice that the wind within the moisture plume encounters land at an angle that is nearly perpendicular to the coast, a feature that can cause intense rainfall. Lastly, we play through the MRMS accumulated rainfall estimate and observe how the western coast is doused with up to 12 inches of precipitation as the AR works its way from north to south over the time period that we observe. These heavy rainfall events produced flooding and landslides in California. The University of Maryland continues to develop new capability to analyze three-dimensional Earth science datasets in virtual reality so that scientists and forecasters can better understand severe weather events.